The rising bubbles of champagne form a visual impression, even before the first sip. A common misconception is that very small bubbles indicate excellence in sparkling wines. In reality, those tiny bubbles are usually just indicative of low carbonation, often from aging, which could signal a traditional method sparkling wine that's intentionally aged, or a bargain bottle that sat untouched for too long. Bubbles aren't just for show, they carry aroma and shape mouthfeel. As part of my slightly questionable hobby of reading random academic papers, we're looking at a review paper. It's titled, Decoding the Visual Aesthetics of Bubble Trains in Sparkling Drinks, and was published in Current Opinion in Food Science. Rather than providing new research, the author summarized the existing science of rising bubbles in sparkling drinks, offering facts you can use to impress your friends at the next dinner party. Every rising bubble has a beginning, and that beginning is at a nucleation site, which is simply a fancy word for a tiny spot where bubbles can start to form. Gaseous germs in the liquid and microcrevices in the glass can serve as nucleation sites, where dissolved carbon dioxide, more commonly known as carbonation, begins to accumulate. These germs are not the microbial kind that require hand sanitizer or singing Twinkle Twinkle Little Star. It's a technical term. As for microcrevices, these can be tiny imperfections that exist naturally in the glass. They can also be deliberately introduced by a glassmaker as controlled starting points to ensure that bubbles form consistently and predictably. The shape of a nucleation site affects how often bubbles are produced. For example, nucleation sites with a smaller radius of curvature form bubbles less frequently. Even within the same glass of champagne, bubble trains with different frequencies can coexist. Once a bubble begins to form, surface tension holds the bubble in place at its point of origin. Buoyancy eventually wins out, and the bubble breaks free and begins its ascent. It expands like a tiny balloon as dissolved carbon dioxide in the surrounding liquid diffuses into it. In a glass of champagne, a bubble can multiply its volume by up to 1,000,000 on its journey to the surface. The number and size of bubbles in a given bubble train depend on how much dissolved carbon dioxide is present in the liquid. Carbonation is highest immediately after pouring, but it steadily escapes into the air. As a result, bubbles gradually become fewer and finer. This provides a simple counterpoint to the common misconception that smaller bubbles automatically signal higher quality. In this case, it's just a glass of sparkling wine that's now a little bit flatter than when it was first poured. More broadly, smaller bubbles indicate lower levels of dissolved carbon dioxide. That can be a consequence of aging, but aging is not a reliable hallmark of quality on its own. One reason older sparkling wines tend to produce smaller, less frequent bubbles is the slow loss of carbon dioxide through cork stoppers during prolonged aging. Rising bubbles also play a direct role in aroma. When they burst at the surface, they release tiny aerosol droplets into the air that help carry aromatic compounds to your nose. Larger bubbles can create an initial surge of aroma, but that effect fades quickly. A steady stream of finer bubbles does a better job of sustaining aroma over time. Dissolved carbon dioxide also shapes mouthfeel. Large bubbles, or excessive effervescence, can create a sharp carbonic bite that can be unpleasant. Once bubbles are rising, they often organize into clean vertical columns instead of meandering through the glass. When bubbles remain neatly aligned like this, it indicates lateral stability. In sparkling drinks, that stability is mainly governed by two factors: bubble size and what else is present in the liquid. There is a critical size beyond which bubbles become unstable. In champagne, bubbles larger than roughly 2 millimeters in diameter no longer rise straight upward. Instead, they begin to oscillate, ascending in zigzag or spiral paths. Champagne and other complex sparkling beverages contain compounds originating from things like yeast and grapes. These act as surfactants, coating the surface of rising bubbles and slowing their motion. This surface coating suppresses sideways movement too and helps stabilize the bubbles, allowing them to rise in orderly, persistent bubble trains. As a result, neatly aligned bubble columns are far less common in surfactant-poor beverages, like sparkling water or soft drinks, where bubbles more easily become unstable. Otherwise identical bubbles behave differently under changing external conditions. Differences in ambient pressure, like those caused by altitude, directly affect both bubble formation frequency and the diameter of the resulting bubbles. For example, If ambient pressure drops from 1 bar at sea level to 0.3 bar at the top of Mount Everest, nucleation frequency nearly triples, and bubble diameter increases by about 55%, roughly quadrupling in volume compared to sea level. One champagne house even hosted an over-the-top tasting in a hot air balloon, letting participants experience firsthand how bubbles changed while floating from sea level up to 10,000 feet. Gravity also influences bubble trains. Lower gravity slows their rise without changing bubbling frequency, letting bubbles grow much larger. For instance, a bubble on the moon would be over 3 times more volume than on Earth, since lunar gravity is just 1/6 of ours. The authors also note that parabolic flights could be used to study how gravity affects bubble dynamics. These specialized airplane maneuvers create brief periods of weightlessness as well as periods of increased gravity. It's an expensive way to fly, but still far cheaper and more practical than an actual trip to the moon and beyond. The authors focused on Champagne, which isn't too surprising given that their university is in the Champagne region of France, but they also show how the same bubble physics appear in a different beverage. Their inclusion of beer is commercially relevant, as beer is the largest global alcoholic sparkling beverage market, almost 100 times larger than the 2 billion liter sparkling wine market. Soft drinks are even larger, but still a similar order of magnitude. A pair of equations predicts how often bubbles form and how big they grow as they rise. We can skip the math and just get a sense from the variables. Many of these we've already touched on, like the amount of carbonation in the glass, the radius of curvature of the nucleation sites, ambient pressure and gravity, and the distance the bubble travels. There are also common properties of fluids, such as temperature, density, surface tension, and viscosity. Finally, there are 2 coefficients: Henry's constant, which describes how much carbon dioxide can dissolve under pressure, and a coefficient generically named alpha, which accounts for the combined influence of the glass wall distance and surfactants, like we previously discussed. Considering the properties of champagne and beer at their respective tasting temperatures, and assuming the bubbles travel a similar distance, beer bubbles are theoretically twice as fine as those in traditional method champagne at the start of tasting, contrary to popular belief. Let's run it back. Bubbles start at tiny nucleation sites. External factors like pressure or gravity change bubble size and frequency. Bubble size and surfactant compounds impact whether bubbles rise in neat columns or meander. Smaller bubbles don't necessarily mean a fancier champagne. It might just mean an older one. Bubbles that are too large or too effervescent can be unpleasant. Now you can impress your friends with tiny science quips while enjoying a tasty sip.